Okay, so we have gone ahead and created this whole system for the first floor, and things are looking pretty good here. The good news is if you go through and you go have a building which is stacked up and has several different layers where the bathrooms are all right on top of each other, as they are in most buildings, you can copy and paste things up. Not only the plumbing fixtures in the walls, you can actually copy up the whole piping system too. So if this were a multi-story building, let me zoom out here a little bit. I could do something like this. I could say, let us grab all these things and grab them this way instead so I can get them. Okay. What I am not going to copy up are the risers, because the riser will actually be one continuous piece. So I'm going to control click, get rid of them in my selection. Or shift click, excuse me. Even that little elbow connection. What do I need to do? I'm trying to think about the best way to do this. I'm going to drag click through that way. It's going to sound really weird. I drag click to grab it all. Now I'm going to, I'm going to shift click and drag the opposite direction to get rid of them, the risers. So if I shift and hover just over those, it'll subtract out just the riser pieces. So, boy, it sounds complicated, but it really isn't. As I drag, I'm getting everything that's copied it all through there. As I come this way, I'm only going to grab the things that are within the bounding box, okay? And shifting is subtracting from the selection as opposed to controlling. So, if you can handle all that, you did good. Copy of the clipboard, paste aligned, aligned to selected levels. Let's put it up on level 2. I got my level 2 bathroom hanging around in here. Yeah, I could have done that really for all the different levels. But the nice thing is now, I can extend my riser up, extend the blue riser up, extend the red riser up, and do all those little joins to it. So green just needs to connect into the green riser. Blue is going to connect into the blue riser. Interesting. I'm not sure what's going on up here at the top of my riser stack, but this doesn't look right. I need to separate that. That's not right. Something happened that they just weren't supposed to get together. Okay, for that last one, you might remember I had to go through and put in a little side link to make it work. Not there. Systems, piping, domestic hot water. That's a particularly bad way of doing it. Try it again. Oh, it's because I'm still measuring relative to level 1. Let me say level 2 instead. No, it's fighting with me a little bit. Because when I put in the pipe, it's not level 1 minus 5'2", it was 410 or whatever it was. You still have to give it some help. Okay, there it was, joined on in. Now, this isn't just a matter of physically connecting all the systems together. You can also go through and use the information in the model and how things are connected to drive the engineering behind this. So, for all these little guys that you've put together, they're now part of a system. You have a sanitary water system, you have a cold water system, and a hot water system. You go into the Systems tab, you can actually find, let me see if I can find, the easiest way to get to it. I'm not seeing it there. If I tab on the blue pipe, you'll see that it'll eventually get to the whole system. There's something called the System Inspector. Let me show you an easier way to get to that. If you go to the View tab and choose User Interface, you'll find Systems Browser there. You can see there's some notion of different piping systems in here. You'll see that there's some sort of domestic cold water system, domestic hot water system, domestic or sanitary system, and if you go expanding this browser, expanding the tree, you'll start seeing, oh, just how many flow units are needed to be supplied in each of those different systems and really what's taking you up. So currently my cold water system, if I route it this way, has to be able to provide up to 51 gallons per minute. My hot water would have to be able to provide 71 gallons per minute. And using this, you can start actually doing the calculations about how big the pipes need to be, what the pressure needs to be to supply all the systems. So it's not only just connecting it together physically and checking for interferences, but you can actually start designing the system itself, how it has to perform. So we can get into just how you do that analysis too. Okay, so that's the basics of plumbing. Let me pause there for a second. Is the plumbing sort of making sense? Okay. Generally what happens is, if you can handle the little rules about the physics, about where you can connect things, everything's going to be good. But the only time we get in trouble again is really if you have, two different pieces, they want to connect, and there just isn't enough room to make the connection. In fact, you might remember as I was messing around back trying to make that connection the first time, it wouldn't let me make the connection just because the two pipes were so incredibly close together that it just didn't see any way to put an elbow in the bend in there. So back them off a little bit and then you'll be okay. Okay, let us then stop with plumbing for just a second, or for now, we'll suspend that, and instead think about the notion of HVAC systems, because they're the other parts, the heating, ventilating, and air conditioning systems that are in buildings that we want to start thinking about designing too. So let's think about how they work. Okay, even the whole term HVAC is kind of an interesting one. So again, heating, ventilating, aircon. Okay. And there's really a couple different aspects going on here that these systems have to go through and meet. So different things that are happening within these. There's some notion of really the comfortable range of temperatures for any room and any application that you want to always maintain. And the way that tends to work is if we go through and follow the temperature profile in a room, if there's a bunch of us, people, computers, equipment, things in there, over time, it'll start rising. The temperature will start rising. Okay. What'll happen is we'll get to the top of something we consider the comfort range, and as soon as we hit that top or exceed it, okay, we actually start applying cooling to bring ourselves back into that range. Okay, so we cool. Or what happens at the other end of the comfort range is the temperature drops, we're sort of back within the comfort range. At night it gets cold, we're losing a lot of heat from the outside, the building gets cooler and cooler. We drop below. What ends up happening is we need to apply some heat to bring ourselves back up. But really what tends to happen is that we're just trying to keep you within that comfort range. And how we actually set that comfort range, what that is, the set points really has a huge impact on our energy use in the building. So if our comfort, set point, if we'd like it to be somewhere around 76 degrees in here, this might be anywhere from 80 degrees to 70 degrees or something like that. It's going to be, it's really, what is the temperature at which when it gets so hot we want to turn on the air conditioning, or when it gets so cool we need to turn on the heat. There's going to be some range in there, and we can actually vary that quite a bit. We encourage people now in their homes to say that, this is actually pretty warm. Let it get down to 68 degrees or even 66 degrees. Let it drop down much cooler because that consumes a lot less heat when that happens. It tends to be fairly uncomfortable for a lot of people, so you wear your sweatshirt, you wear your sweater and things like that. You'll see I'm usually wearing a sweatshirt of some type because I'm I think rooms tend to be too cool a lot of the time. Same thing on the heat side. If we could let that go up to 82 degrees, yeah, it'll actually save a lot of energy because we'll be doing less heating or cooling. Now, when we say we're heating or cooling, what we tend to do is we have some sort of a system that is either heating, adding heat to air, or cooling air that's passing through. We have to have a way to get that heating or cooling into the room where you are. And one of the most common systems we use is something that's called forced air systems. So we're pushing air through the building. We have this opportunity, basically through some sort of air handler. We have some sort of air coming in. I'm not sure just really what its temperature is on this side, but it's coming into that thing. And based upon what we do inside the air handler, whether we're going to heat it up or cool it, air is going to be emerging on the other side at some other temperature that we want to be using within the building. Okay? And what tends to happen in these systems is we'll take the air from the air handler, we'll send it on over to the room where we're going to use it. Hopefully it'll keep us within the set point over here. What happens though is that, we need to continue to supply air to the room. So what we'll do is actually pull it back out of the room and take it back in. And that's the basis of a lot of forced air systems. So the way we'll talk about this is we'll say that this is the supply side. We're supplying the room with air. And this side over here is the return side. So let's just think about this for a second. The reason we tend to recirculate air through the room is that if we were always pulling in outside air, like on a cold night like tonight, if we were pulling in the outside air constantly, it's a lot colder out there, so we'd have to do a lot more heating to get it up to where we need it to be. So it's probably better to take the air that may have cooled down a bit in here and heat it back up again, as opposed to what's outside. Now, on a summer evening, it might be actually cooler out there, so we'd actually prefer to grab that air and bring it in, as opposed to dealing with the air in here. So there's this constant kind of change between where we're getting the air. Are we recirculating it, or are we getting it from the outside? And that really depends on what the temperature in the natural environment is relative to the temperature inside here. And really where we want it to be. So good systems try to take advantage of that. Good systems in buildings built in the last several years. Older buildings aren't smart enough to do that. They pretty much have it either almost always recirculating or the system's off. There's very little control over that. So we've learned to be smarter about that. But there's always air moving through a building. Let's think about that, because that actually, this ventilating piece is one of the most interesting aspects of it. People don't realize that so much of what we do is really not based on the heating and cooling, it's based on the ventilating. Okay, so let me kind of bring up a chart. Give you a sense of what the driving considerations are. Okay, we need to change the air in a room. And the reason we need to change it is if you don't have the air changing in a room, the room sort of gets heavy or still. Or you ever walked into a room and it's not necessarily hot, but it kind of feels like a locker room in there. It just sort of, the air's just been hanging around too long. It needs to kind of keep on moving. So to keep spaces just fresh, you want to have them changing about 4 times per hour. So in an average space, 4 times an hour, in an average office space, 4 times per hour is minimum. It might be much greater than that. What is it? Drug shops, engine rooms. They don't have to change very much because they aren't occupied as much. Courthouses. Computer rooms, they want it to change more. There's a lot of heat they're trying to carry away in there. In big rooms where there's a lot of assembly, like in a church, or in an auditorium, you'll see it's higher. You need to sort of keep on the air moving more when you have a lot of people in the space. Go ahead and kind of keep it feeling good. Some things like, bakeries, where they go, they're 20 times, or bars, 20 to 30 times. Yeah, I'm not sure if that's still true. It used to be because bars were smoky kind of places that had a lot of pretty noxious fumes in them. So it may no longer be that bad. but oh, even in a dining room in a restaurant, 12 changes an hour. That's because, oh, you're eating your dinner. You kind of want to be enjoying the aroma of your dinner, not the dinner like 3 booths down or something like that. So there's this whole notion about changing air. But let's see what that actually might mean to us in a room like this. Okay, so this is all based on number of room changes per hour. Let's relate that back to a measure that they actually use when sizing systems, which is CFM, which is cubic feet per minute. Okay, so if we were changing the air in this room, let's think about this room. How tall is this room as best you can guess? Oh, anyone, go ahead. I don't have the absolute number. I always guess a slightly different number. But, you know, it's okay. It's clearly taller than 6 feet. You know, what is it? Is it twice as tall as I am? Maybe? Okay. Maybe 12 feet. I mean, I'd guess. How about, how wide is the room? Yeah, I'll give you my trick for doing that. I always count the ceiling tiles. So ceiling tiles are each 2 feet wide. It's a pretty good way of really quickly getting an estimate. And, what's that? Okay, so about 20 that way. How about in this dimension? I thought you guys were counting in the other direction as they were counting this way. So how many tiles is this one? Around 36? Okay. Okay. So either one of my mathematicians in the room or someone who has a calculator real quickly, please multiply those things together. Oh, you just happen to have your calculator handy. Very good. 3640?
8640.
Like that?
Yeah.
Okay, so that is the number of cubic feet. So or feet cubed. Okay. Now, there is a certain number of air changes per hour. Okay, minimum would be for, let's say we're going to go for, something a little bit more. Well, even like this is a computer room. Well, that's a computer room in the sense of like a server room or something like that. Well, maybe, somewhat good. Let me say I want to have a goal of, say, 8 air changes per hour. Okay, so if in a single hour I wanted to change the air in here 8 times, I'd say times 8. Okay, so still have your calculator here? Oh, don't put it away. I'm going to make you do one more thing.
69,120.
69,120? Okay, now that's per hour. Okay, so, oh no, excuse me. What did we just do there? The 8 air changes. That's okay. That's air changes. Okay, yes, and this is cubic feet, blah, blah, blah. Okay, and now I basically want to go through and divide by, it's like 60. Cubic feet, that's per hour, that's cubic feet. 4 air changes per hour. Oh, and I want to get back to minutes. That's what it is. I'm losing my math here. So this is 8 changes per hour. Okay. So if I divided that through by 60, they give me the number of changes per or cubic feet per minute. 1152. Okay, so that's cubic feet per minute. Okay, so I want 1152 cubic feet per minute moving into this space. I also want 1152 cubic feet per minute moving out of this space. Yeah, okay. And why does that number strike me as so large all of a sudden? But it's not. Okay. Yeah. The reason I want it moving in and out of space, let's talk about that. Like, why do we care about it being the same flowing in and flowing out of the space? What would happen if more air were flowing into the room than we were pulling away from the room? What would happen inside the room? Yeah, it'd be like filling up a balloon. So after a while, different things would happen. We'd be pushing stuff out. It would start to seeping out through under the door and every place like that. But if you've ever been in a building where it's kind of hard to open the door, you're really you're fighting against pressure in the building. So if there's too much positive pressure in the building, that's not good. Okay, it makes for sort of a very airtight building, but you try not to have that number be very much out of balance, or you start having problems where doors swing open automatic, by themselves, or it's just to be an uncomfortable space for people. Same thing on the back side. What if there's like really not enough pressure in the roof? We're pulling more out of here, okay, than we're supplying. Okay, so if I was actually sucking more out of here than I was providing, either this is going to depressurize like an airplane, okay, and everyone's ears are going to pop, or we're going to start having that problem. But this room's not so airtight. It's not going to do that in the same sense. So what's going to happen to make up that air? We're not getting it from the HVAC system. Where do you think the air comes from? It's got to come through. Can you think of any openings? Is it going to come through the walls? Will it come? How about if there's windows and stuff like that with tiny cracks around the windows? Under the door, it'll start coming that. We start having this problem where we get infiltration, okay, where we're pulling in air, and that air may be colder or not temperate to the way we want the room to be kind of conditioned. So we start sucking in this air, and actually, since it's not conditioned, it's sort of working against our heating and cooling balance in terms of what we're trying to achieve. So the best thing is to have these things balanced. If you have in and out balanced, everyone's sort of happy, no one's ears are popping, you can open the doors. All this kind of good stuff happens if you have these systems balanced. Okay, so as we think about creating a system, keeping a balanced system with both sides sort of works. So in order to supply this air, you're going to find out there are these things called air terminals, and you can actually see some of them around here, although it's harder to spot. Like that's a return air. That might actually be a supply air there too. It's hard to tell here because we have the chill beams. They sort of throw all my discussion off. But there's one. There's one over there right above Chris's head too. In terms of what's going on. Okay. I imagine what's happening in this room is there's actually one that is supplying over on this end of the room, one that's actually removing air over on that side of the room. Either that or those are both returns. It looks like almost for the chilled beams, there could be some air coming from those. I'm trying to think how the technology works. We have to kind of keep them working together. Let me kind of show you an example of kind of a more typical office layout. Switching back over to that just MEP model for that little office building. If I go taking a look at the system up at the office level, okay, let me do a little coloration of this to give you a sense of how this is actually set up. So I'm going to show you something called some filters we can set up, which will actually make it look a little bit better in terms of, let me turn the supply system and the mechanical on. And for that, I'm going to give it a color, kind of a reddish pinkish color. Then I'm also going to add a little coloration to the return system. Okay, and I'll think of that kind of as a blue color because I tend to think of the supply as often heating. Okay, so this might give you a better sense of how the system works. Let's show you what's going on. Actually, I have two systems in place here. See if I can sort of see them both. Oh, let me see if I can even it's very interesting to me about the way they're displaying right now because I think that looks very funny. Oh, we'll go with it. I'm not sure what's causing the, you call it almost the scratchiness between them. I don't know. Okay, the red system is actually supplying air. The blue system is taking air away. And if you look at the way this is designed, and this was actually designed by students a couple of years ago for this building, the way things are working in this system is air is being supplied to the rooms. We often supply the air to the rooms close to the windows, close to the outside surfaces, because the outside surfaces are really where if there's cold on the outside, it starts getting cold. If it's hot on the outside, it's getting overly hot there. So you'd like to actually supply the conditioned air there. That's where it makes the biggest difference. And then in terms of returning the air, often we put that closer to the center of the building, back towards the hallways, because if this were a system like that, I'd probably supply the air over here and return it over there. What I'm just trying to create a draft. Okay, so from the windows and pull it back away, and it's going to go up to the air handler. So put it where it's going to do the most good, and then draw it through the space and carry it away. Okay, so you rarely put the supplies and the returns right next to each other. You like them kind of be separated a little bit so that you have, kind of you're drawing air through the space, okay, and getting the most benefit of it. So each of these different little air handlers right here has a rating to it. They are all rated by basically how many cubic feet per minute they can put out. So for one of these little air handling terminals, okay, that's in a 2x2 ceiling like this, an average rating for something like this is about 500 cubic feet per minute. Okay, so if I wanted to go through and supply 1,152 cubic feet per minute, I could put 2 in there and be a little less than 8 changes an hour. I could put 3 in there and I'd be more than 8 changes an hour. Okay, but that's how you basically design these systems. You basically figure out how much overall airflow you want through here. You have to sort of ultimately divide through by just some even increment, and then you put in that many terminals. So if I wanted to put 2 in here, I'd probably put 2 on this end. I'd also have to put 2 returns. Okay, but that's how you figure that out. It's really, that's, all of HVAC science in 20 minutes. That's really the high level about how this sort of works. And that's how you can actually determine how many you need in any one space. So in PBL, when you're designing your MEP systems, you'll do something like that. For each of the different spaces, figure out how many air changes in that room, how big that room, and put the right number of terminals in each room to give the number of air changes needed. Yeah?
So is this just assuming that the air is constantly running through rather than having certain points where it's on and off?
A very interesting question. Yeah. In residential systems, we're actually pretty sloppy about this because when the heat's not on, the air is not moving. And we'll say, we're hoping there's just enough draft through the house and infiltration to kind of take care of the ventilation needs. In commercial buildings, it's much, much stricter about this. So even if we're not heating or cooling, they'll often be pushing air through the building, okay, even if it's not heated or cooled air. So if you ever come into an office building on the weekend when they think no one's working and you're the one person there on Saturday, again, it's that still heavy thing going on. It's not just depressing that you're there on Saturday. The air even feels different because it's just not moving. Okay, so, it is sort of based on the notion that air is always moving, or at least should always be moving at the times when the occupancies you're trying to keep safe are there. So like that church or something like that, that's how much we need on Sunday morning. It isn't necessarily what you need on Thursday night at midnight. Okay, it's when the congregation's actually meeting. Same thing with auditoriums. So that's why it's really good in most buildings that are well controlled. You can have the ventilation system controlled by sensors so that it's only blowing all the air when the room's actually being used. It can be still, because if this room is still and no one's in here from 2 to 4 in the morning, that's okay. Computers don't care. But as soon as you're here at 8 in the morning, you light and start moving again. Okay, so what does this all mean about computer modeling? Let's kind of tie that back into that system, how you actually do a computer model for something like this. And it's actually very similar to running the plumbing systems in that, on the ceiling of this building, there are all these little terminals, and some of these are terminals for return, some of these are terminals for supplying. And it's all a matter of going through and putting those things together. So how about, I'll just do it right in this building. Oh, I'll take out some of these terminals and show you how they get placed, and we'll continue this again next time. Kind of show you a lot of the same concerns apply. I'm just sort of simplifying the system a little bit so we can add some more things to it. Actually, that was pretty ugly. So I took out some terminals. Let's kind of recomplete the system. So here's the deal. I want to put a couple air terminals in there for supplying. I want to put a couple air terminals in there for returning. And the terminals all show up under the Systems tab. Oh, I got to find them. There's air terminals. If you check out the types, there are different types, supplies, some returns that have different types of connection characteristics. I'm going to put some supply ones in here now. Okay, in the same sense of needing to go ahead and give them some sort of displacement, even for these, I need to sort of say what level it's going to be on, and then what the offset's going to be. See if I can adjust this. It's on level 3, but I want that to be at level 3. Try that again. And I'm going to give it some displacement. You tend to like to have the terminals right at the ceiling plane level. So even if I got 12 feet in here, well, here they'd be 12 feet in the ceiling plane. But you want to put them at wherever the ceiling plane level is going to be. And you can even host these on the ceiling if you like. I'm going to put these in at 9 feet above the floor. And just because it's so hard to draw that in 3D nicely, I'll do it this way because it'll be a little easier to see what I'm up to. So this is going to be the returns. I'll tend to put them close into the system. So again, here we are. It's at 9 feet, 500 cubic feet per minute. Okay. Let's go ahead and put in some of these terminals. And instead, oh, actually, those were the supply, weren't they? Those are supplies. For supplies, I decided I was going to put them out towards the window. Okay, returns now. Air terminals, return diffuser. Let's say from level 3, again 9 feet off the floor. I'll put them in close. Okay, let's push those over a little bit so they're not kind of so immediately on top of each other. Oddly, you can just go ahead and choose those and start saying connect into and tie them in. In this system, I already have the main supply and main return duct lines running here. Next time we get together, we'll show you how you run all those. It's very much like running the laterals and the risers and all that kind of stuff. But let's just show you how the connection stuff works. If you try to connect ductwork to the supply ducts, or connect the terminals to supply ducts, if you're going to have any trouble at all, it'll probably be related to the fact that ductwork actually turns out to be very fussy in that it's made of sheet metal. If you're going to make an elbow or a tap or some sort of connection, there's certain minimal clearances that are often necessary to go through and have a bend that's considered a smooth bend that has enough curvature to it, not really create some sort of pinch point. So there's a whole science to the types of connections you can put in there. But in general, the principle looks like this. And again, we'll sort of play with this some more. I can say that I want to take ductwork, and if I want to extend off of the return line, I can just start with the return line and pull a piece of ductwork out. Now, I'll drop it right there for now. Oops. Let me say that you are going to be a return air piece of ductwork. Okay. In the same sort of sense, let me put another piece of ductwork over here. And make you a return air piece of ductwork. Let's talk about whether you can really join that final piece. As you go through and you put together systems like this, you may be actually be able to get a nice hard join between the ductwork and the terminals, but it's sometimes a little bit difficult. And if it's having trouble joining them, it really has more to do with, just given the level of this and the height of that, there may not be enough room to kind of put the bend in and kind of do things the way you want. So we can either try just changing the height of the supply system, okay, so that it is at a better elevation relative to those, so you do have room to go through and make those connections. Or if you have a very limited ceiling space like we might have in this building, what you can do is actually use a slightly more flexible kind of duct called flex duct. What it lets you do is basically just take something like this, connect to that, and it makes it out of a very flexible, easy to work with kind of duct that has a lot of bendability to it called flexi duct. It's kind of like dryer hose that you have out of the back where it's foily, it's got a coil of wire in there. It's very, very flexible and adaptive. The reason we like to use it is, besides being able to kind of handle all sorts of geometries, a little bit of flexibility, sometimes if you don't have very precise control over just exactly where those terminals are going to end up, this gives you that ability to kind of be a few inches off this direction or a few inches off that direction, whereas if those are all hard ducts, you have to be very, very precise. They really need to be exactly where they need to be because they're manufactured to be that way. We don't like flexi ducts since it's less efficient than the smooth-walled, hard metal ducts, so there's an efficiency loss in that. So when we do use flexi duct, we kind of keep it in very small little lengths, 3 or 4 feet. It's those last few inches, not a big old run of it. Okay, that's available for doing that. But we'll play some more with these next time in terms of running these ducting systems. But it really is all about, in here, the same sort of thing, just connecting the different terminals together. What we're going to find out about the mechanical systems or the HVAC systems that really starts to be the big concern is, the terminals, we can get those where they need to be and plan that out. Where we really start getting into trouble or we have to do a lot of work is just trying to figure out some strategy for all these ducts which are trying to run through the ceiling and crisscross past each other, and the structural members which are also in that small space, how to get them all to pass and not conflict with each other. Really gets to be probably one of the biggest challenges we face when we're designing buildings. So let's leave it at that and say we'll pick that up next time. It really becomes all about this funny issue of, in that limited space, how we get all those things together, and ducts are one of the hardest ones because they don't just like to bend around everything very easily. Okay, so let's stop there for tonight and go out and have yourself a great evening.